All right, this is going to help you with number 12 on the summative review. So I have a potential energy graph versus the internuclear distance. We saw this at the beginning of the year when we talked, or at the beginning of the unit when we talked about why things bond. And we talked about if we had two hydrogen atoms very, very close together, that's a very not favorable energy because they'll repel. But then as we get farther and farther away, we move those hydrogens farther and farther away, there's no attraction at all. And there's this kind of happy place where when the two atoms are bonded together at the appropriate distance, we are lower in energy. So on our potential energy graph, something down low is actually representing basically the energy of that bond, and the more exothermic it is, the more favorable it is for those two atoms. And this axis here is representing the distance between the atoms. So we have some choices: hydrogen, nitrogen, and oxygen. And if you look between hydrogen, nitrogen, and oxygen, hydrogen is going to be the smallest atom. It's in the first energy level. Nitrogen and oxygen are both in the second energy level. So right away, I know that hydrogen is able to get closer to the other hydrogen atom it's bonded to. And so in terms of the internuclear distance, the atom that will have the bond occurring at the shortest internuclear distance is going to be my hydrogen because it's the smaller atom. So that means X has to be hydrogen. So that eliminates options C and D. And then we're going to look at nitrogen and oxygen, and those guys are both in the second energy level. So then we can look at the bonds. And so what I see here is oxygen in the Lewis structure has a double bond, which we know is a little bit longer than a triple bond. But as I look at this graph, what I notice, so if I go from here up and mark the internuclear distance, and I go here, there's not a huge difference or separation between those two, but what stands out to me is that one of these has a very, very exothermic potential energy, which is graph Y. And I know a couple of things. I know that a triple bond is very, very strong, meaning I would have to put in a lot of energy to break that. So this triple bond, this little dip right here, is representing the triple bond, and this one that looks more similar to the hydrogen is representing the double bond. Understandably so, when we're talking distance-wise, right, we know that an oxygen bond is longer, so you can see as well that the oxygen bond on the Z graph is a little bit bigger than the triple bond, which is shorter, but there's not a huge difference compared to what we see with the hydrogen because the hydrogen atoms are so small. So again, you can tell based off the length of the bond, but you can also tell based off the energy. A triple bond is much stronger than a double bond. But before I looked at the type of bond, double, triple, or single, I needed to see the size of the atom. So hydrogen automatically is going to be the shortest bond because it can get closer to the other hydrogen atom. So hopefully that helps in narrowing down why A is the best answer.